Hello there, and welcome to the Sleepless Scientist, a quiet little corner of the cosmos where your thoughts can rest, and where science becomes a soft lullaby for the night. Tonight's journey will take us into the mysterious realm of quantum physics, a place where reality itself seems to hesitate, holding its breath until someone looks. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these gentle explorations comforting. And when you're ready, leave a comment letting me know where in the world you're listening from and what time it is for you right now. It's always a joy to imagine people gathered across time zones, night owls in New York, early sleepers in Tokyo, dreamers in Sydney, all quietly joining the same story. Now, if you haven't already, dim the lights, fluff your pillows, maybe even switch on a small fan for a soft background hum. Let your shoulders relax, let your breath slow down. You don't have to hold on to anything here. Tonight, we're going to wander gently into the strange and beautiful world of quantum physics. And if your mind begins to drift, that's perfectly fine. Let it wander. We'll still be here, unfolding the story softly, like a blanket being laid across your shoulders. Quantum physics is, in many ways, the most successful and yet the most puzzling framework we've ever built to understand nature. It explains why the sun shines, why matter holds together, and why technologies from lasers to smartphones to MRI machines even work. And yet it comes with a twist. The rules it describes seem to make sense only in the language of probabilities, not certainties. Things exist in maybes, in overlapping possibilities, until something, or someone, interacts with them. Only then do they appear definite. That's why people sometimes say reality collapses into shape when we observe it. It's not that our eyes or minds control the universe, but rather that the very act of interaction forces a choice out of many possibilities. Imagine a coin spinning in the air. While it spins, it's not really heads or tails. It's a blur of both. Only when it lands in your hand do you see a single outcome. That spinning blur, that state of many possibilities at once, is the everyday cousin of what quantum physicists call superposition. But don't worry. Tonight we won't be chasing after equations on a chalkboard or memorizing dense symbols. Instead, we'll be painting with words, using images you already know. The way your coffee slowly cools on the table, the way shadows dance in the late afternoon, the way music swells and then falls quiet again. These familiar moments are little doorways into the quantum world because they let us feel rather than just calculate what these strange ideas mean. So where do we begin? Let's start by remembering how physics looked before the quantum revolution. For centuries, the universe was thought to be like a grand machine. Isaac Newton had shown that apples fall and planets move by the same rules, and those rules felt as solid as the ground beneath your feet. If you knew where an object was and how fast it was moving, you could predict exactly where it would be tomorrow, or next year, or even 1,000 years from now. The cosmos seemed like a perfect clockwork. But at the turn of the 20th century, little cracks began to show in that certainty. Physicists noticed that when they heated objects, like the inside of a furnace or the filament of a light bulb, the way those objects glowed didn't match the predictions of Newton's physics. The colours of the light refused to fit the equations. This was called the ultraviolet catastrophe, a dramatic name for a simple but stubborn puzzle. According to the math, hot objects should give off an infinite flood of violet and ultraviolet light. Yet in reality they didn't. It was Max Planck, a German physicist, who reluctantly suggested a solution in 1900. He proposed that energy doesn't flow smoothly like water, but instead comes in tiny chunks which he called quanta. Imagine light not as a continuous river, but as a string of droplets. At first, Planck thought this was only a mathematical trick, temporary patch to make the equations work. But it turned out to be the first step into an entirely new way of seeing reality. A few years later, Albert Einstein took this idea further. He he explained something called the photoelectric effect, where light shining on a metal surface could knock electrons loose. According to classical physics, the brightness of the light should be what mattered, but experiments showed it was the colour, or more precisely the energy of each light particle, that determined whether electrons would be freed. Einstein proposed that light itself is made of little bundles of energy, which we now call photons. In that moment, the wave of light also became a particle, and the neat categories of waves and particles began to blur. From that point on, the story only grew stranger. Over the decades, experiment after experiment revealed that particles could behave like waves, waves could act like particles, and things could exist in multiple states until they were measured. Physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger struggled not only to calculate what was happening, but to understand what it meant for reality itself, and that is where our journey will take us tonight. From Planck's hesitant step to Schrödinger's famous cat, from the uncertainty principle to entanglement, from quantum tunneling to the quantum computers of today, we'll walk slowly through the landscape of quantum physics. But don't worry if you feel drowsy as we go. In fact, I hope you do. The quantum world is vast and strange, but it is also gentle when explained with care. Each experiment is like a dream told by nature, a dream we are still trying to interpret. So let your mind float, let your eyes grow heavy if they wish, and trust that the story will still be here, patiently unfolding, like stars appearing one by one in the night sky. Because sometimes the best way to explore the deepest mysteries is not with frantic calculation, but with quiet wonder, and that's exactly what we'll do together. If you close your eyes for a moment and imagine the world as people once thought it was, you might picture a universe of certainty. Planets glided along fixed paths, like gears turning in a perfect machine. Apples fell from trees at predictable angles. Cannonballs traced smooth arcs through the air, and the whole cosmos seemed like a grand clock, each tick and tock determined by unchanging laws. Isaac Newton had written down those laws in the 17th century, and for more than 200 years they seemed unshakable. If you knew where something was and how fast it was moving, you could, in principle, predict its entire future. It was a reassuring picture, a universe governed by clarity. Yet beneath this polished surface, there were hints of strangeness waiting to be uncovered. Imagine a glowing fireplace on a winter night. The embers shift from deep red to bright orange, then to dazzling white as the heat increases. For Newton's world, this changing colour should have been simple to explain. But when physicists of the late 19th century tried to predict the exact way heated objects glow, they ran into an impossible problem. Their equation said that as things got hotter, they should radiate an infinite amount of energy in violet and ultraviolet light. If the math were right, every stove, every lamp, every warm cup of tea would blaze with unbearable brightness in invisible ultraviolet rays. But of course, reality was gentler than that. Lamps glowed softly, ovens warmed kitchens, and no one was burned by a flood of invisible energy. This puzzle came to be known as the ultraviolet catastrophe. It sounds dramatic, and in a sense it was, because it meant the most trusted physics of the time was failing at something as basic as explaining light from a hot object. It was like watching a faithful clock suddenly lose track of the hours. Enter Max Planck, a German physicist with a quiet demeanour. In the year 1900, Planck was working tirelessly to fix the equations of heat and light, and in his struggle he stumbled upon an idea that even he considered almost absurd. He suggested that energy could not be spread out in a smooth, continuous way. Instead, it had to come in tiny, indivisible packets. He called these packets quanta. Imagine pouring water from a jug, and instead of a steady stream, it arrives at your cup in distinct droplets, one after another. That was how Planck described energy, not as a flowing river, but as a string of tiny beads. Planck introduced a new constant of nature, today simply known as Planck's constant. Rather than a letter or symbol, think of it as a whisper at the heart of the universe, telling energy how small each step must be. This was not just a number pulled from thin air. It was carefully chosen to make the equations match the observed glow of heated objects. To Planck, it was a desperate adjustment, not a revolution. He even believed it might be temporary, but history had other plans. Only a few years later, in 1905, Albert Einstein took Planck's hesitant step and turned it into a stride. He was studying something called the photoelectric effect, where light shining on a piece of metal can knock electrons free. In classical physics, this should have been easy. Shine brighter light, and more energy should spill out, releasing more electrons. But that wasn't what experiments showed. What mattered wasn't the brightness, but the colour of the light. A dim blue light could free electrons, while the brightest red light often could not. The conclusion was unavoidable. Light was not just a wave, as everyone had believed. It also came in little bundles of energy, each tied to its colour. These bundles were the photons. Imagine sunlight not as a continuous glow, but as a shower of tiny golden coins, each carrying just the right amount of energy to nudge an electron loose. Red light coins are too light to pay the cost no matter how many you collect. Blue light coins, though fewer, carry enough value to open the door. This simple image captures what Einstein explained, that light was both a wave, spreading and interfering, and also a particle, delivering discrete kicks of energy. The photoelectric effect, at first glance, may have seemed like a narrow detail of physics, but it was a doorway into a new world. Today, the principle powers solar panels, turning sunlight into usable electricity. Every time a panel on a rooftop soaks in the sun, it is Einstein's photons doing the work. In 1921, this insight earned him the Nobel Prize, a reminder that sometimes the quiet puzzles of nature hide profound truths. Between Planck's reluctant quanta and Einstein's confident photons, the classical view of reality began to unravel. The neat categories of waves and particles blurred together. Was light a ripple, like water in a pond? Or was it a stream of bullets, each one carrying a tiny punch of energy? The strange answer was both. Depending on how you ask nature the question, light could play either role, or even something in between. This dual nature became the first great signature of the quantum world. It is worth pausing here, letting this sink in like warm tea spreading through your hands. The everyday world seems so steady. The furniture in your room, the blanket over you, the lamp by your side. And yet, beneath all of it, the rules that govern energy and light are not steady rivers, but trembling droplets, quanta leaping in discrete steps. Physics was beginning to glimpse a reality made not of certainties, but of possibilities. From this point, the path would lead to even stranger landscapes. Niels Bohr would reshape the atom into a place where electrons could only exist in specific orbits, like rungs of a ladder you cannot skip. Erwin Schrödinger would describe particles as waves of probability, clouds of chance drifting through space. Werner Heisenberg would show that even our knowledge of position and momentum was limited, blurred by an unavoidable uncertainty. The universe was beginning to whisper a new story, one that left behind the firm tick of Newton's clock and replaced it with the soft hum of probabilities. And so, as we settle deeper into this night, let us remember that the quantum revolution did not arrive with fanfare, but with hesitation. Planck thought his quanta were a trick. Einstein thought photons were peculiar, even as they worked perfectly. The world did not change in a thunderclap. It changed slowly, like dawn spreading across the horizon. One puzzle at a time, one daring idea at a time, the solid clockwork began to dissolve, and a shimmering new picture took its place. The story we are stepping into is not only about mathematics and experiments, it is about how reality itself behaves when we lean close enough to listen. And as you rest, with your breath gentle and your body heavy against the bed, you're listening now, not just with your ears, but with the quiet curiosity that has always been the companion of discovery. Imagine yourself watching the glow of an old light bulb. At first, the filament is dark. Then a faint red shimmer appears, and with more current, the glow brightens into orange, then white. It is such an ordinary sight that it is easy to forget what a mystery it once was. For scientists at the dawn of the 20th century, explaining that simple glow turned out to require breaking open the foundations of physics. Max Planck, often described as a cautious and meticulous thinker, was the first to offer a solution. To make the equations match the way heated objects really shine, he proposed that energy comes in little steps, not as a smooth flow. You could think of it like climbing stairs instead of walking up a ramp. Energy, in Planck's picture, is not continuous. It rises in tiny jumps, each one the smallest possible unit, determined by a constant of nature. This constant became known as Planck's constant, a number so tiny it's hard to imagine, but so fundamental that it marks the scale at which quantum physics begins to rule. Instead of giving it as a symbol, think of Planck's constant as a whisper telling light how much energy each droplet carries. A faint reminder that the universe is not carved out in infinite gradations, but in delicate, indivisible notes. If the world were music, Planck's constant would be the space between one key and the next, setting the rhythm for the song of reality. At first, Planck treated this idea as an uncomfortable trick, a temporary patch. But soon, Albert Einstein gave it a bolder life. Einstein asked, if energy comes in packets, what if light itself is made of these packets? What if the wave of light is at the same time a shower of tiny particles, each carrying one discrete amount of energy? He called these light particles quanta of the electromagnetic field, and later they were given the name we know today, photons. To picture a photon, imagine a drop of rain, but made of pure light. Each photon carries energy depending on its colour. Red light photons are gentle drops, with smaller energy. Blue or violet photons are sharper, carrying more. Brightness, in this picture, is simply how many drops arrive each moment, but the energy of each drop depends only on the colour. This picture explained the puzzling photoelectric effect. When light shines on a metal surface, sometimes electrons are released. Classical physics predicted that increasing brightness, no matter the colour, should eventually knock electrons free. But experiments showed the opposite. If the colour was too red, no amount of brightness mattered. The electron stayed bound. Yet with a faint violet or blue light, electrons jumped free instantly. Einstein's answer was simple and elegant. Electrons could only be freed if each photon carried enough energy to pay the price. Brightness was irrelevant if the individual coins of energy were too small. 1 billion pennies cannot buy what one golden coin can. The effect was so convincing that it won Einstein the Nobel Prize, and it cemented the idea of light behaving as both a wave and a particle. Here we meet one of the great paradoxes of quantum physics. When you send light through two slits, it behaves like a wave, creating ripples that overlap and interfere. But when you look closely, the light arrives in individual hits, like particles knocking on a door. It is not that light changes its mind. Rather, nature insists on wearing both costumes at once, slipping between wave and particle depending on how we ask the question. This duality is not limited to light. Later, it was found that electrons, atoms, even molecules can show the same behaviour. Matter, too, has its wave side, subtle and ghost-like. In the laboratory, scientists have sent streams of electrons through slits and seen the same rippling patterns as if they were waves. They have even done this with giant molecules made of dozens of atoms. The larger the object, the harder it is to preserve the delicate wave-like behaviour, but the principle holds. The entire material world carries within it this hidden dual character. When Planck first introduced quanta, he could not have guessed how deeply it would change our understanding of the universe. He thought of it as a reluctant mathematical trick. Einstein, however, embraced it as a real description of light itself. From their combined insights came the realization that reality at its smallest scales is not continuous but granular, built from steps and drops and packets. To bring this down to an everyday sense, think of a dimmer switch on a lamp. Turn it slowly, and you expect the brightness to rise smoothly. But at the quantum level, brightness is really about the number of photons streaming out. Twist the knob, and you're not truly raising the energy of each photon. You're releasing more or fewer of them. Each one carries its fixed portion of energy, determined by its colour. The lamp's glow is a river of individual droplets, too fine for the eye to notice, but always present. There is a quiet beauty in this idea. It tells us that the universe is not infinitely divisible. At some scale, there is a graininess to reality, like sand beneath the water. You cannot take smaller and smaller steps forever. There is a final rhythm, the smallest beat to the drum of existence, and it is set by Planck's constant. As you lie back and let these thoughts drift through your mind, you might notice how comforting it is to think of the world in packets, droplets, and notes, rather than in chalkboard symbols. The science is real, but it does not demand tension. It invites imagination. Perhaps in some small way the light of your bedside lamp, or the glow of the screen you are listening through, carries with it the echo of Planck and Einstein's insights. Countless photons arriving, each whispering the story of a century-old revolution in physics, a story still unfolding quietly today. Imagine holding a tiny model of the solar system in your hands. The sun sits in the middle, glowing brightly, and the planets circle around in neat orbits. For centuries, this was also how many people pictured the atom. A miniature solar system, with electrons circling a nucleus the way planets circle the sun. It was an elegant picture, and it seemed almost too beautiful not to be true. But when scientists began to test it against experiments, the neat solar system atom quickly fell apart. The problem was this: if electrons were truly tiny planets orbiting a nucleus, then they should constantly radiate energy, like a spinning top that slows down. Bit by bit they would spiral inward, falling into the nucleus. In other words, the atom should collapse in the blink of an eye. But atoms don't collapse. They are stable. Your body, the air around you, the stars above, all of them rely on atoms quietly holding together for billions of years. Clearly something was missing from the simple solar system picture. That missing piece was discovered by a young Danish physicist named Niels Bohr in 1913. Bohr suggested that electrons cannot just orbit anywhere they like. Instead, they are restricted to specific energy levels, almost like rungs on a ladder. You cannot stand halfway between two steps. You must place your foot on one step or the next. In the same way, electrons must choose from fixed orbits, each one corresponding to a certain amount of energy. This idea explained why atoms give off very particular colours of light. When scientists looked at glowing hydrogen gas through a prism, they didn't see a smooth rainbow. Instead, they saw a handful of sharp, bright lines: red, blue, violet, each at an exact position. These lines were the atom's fingerprint. Bohr showed that when an electron jumps from a higher rung to a lower one, it releases a photon with a precise energy, and that photon appears as one of those bright spectral lines. Think of an electron as a musician on a piano that only has a few allowed keys. The electron cannot play every note, only those set by the structure of the atom. When it changes keys, it produces a photon, like a little burst of music. The glowing colours of gases, the shine of neon lights, even the way stars sparkle, all come from these jumps between quantum rungs. Bohr's model was both revolutionary and strangely comforting. On the one hand, it broke with centuries of intuition, saying that electrons live in a quantized world where only certain steps are allowed. On the other hand, it brought order to what seemed like chaos. Suddenly, The puzzle of atomic spectra was no longer mysterious scribbles of light, but a song with notes, scales and harmonies. Of course, Bohr's atom was not the final word. Later, Schrödinger's wave equation would describe electrons not as tiny planets, but as clouds of probability surrounding the nucleus. Yet Bohr's insight remains important, because it was the first time the atom was understood as a quantized structure. The staircase of energy levels, each one neatly arranged, is still part of how we talk about atoms today. Let's pause here and translate this into something familiar. Picture a child climbing a slide at the playground. They can stop at the first step, the second, or the third. They cannot hover halfway in between, because there is no half step to rest on. When the child climbs down, they release energy with each drop. Now imagine that instead of laughter, each drop produces a photon of light. The playground is the atom, the ladder is the set of energy levels, and the photons are the sparkles we see in the spectrum. This idea also leads to the technologies we live with today. Neon signs, for example, work by running electricity through a tube filled with neon atoms. Electrons inside the atoms are excited up the ladder, then fall back down, releasing their energy as light. The familiar red glow of neon is simply the atom playing its favourite notes over and over. The screens we watch, the lasers in scanners, the glow of fluorescent lamps, all are orchestrated performances of electrons climbing and descending their quantum staircases. Bohr's picture also offered something subtle but profound. It told us that nature is not free to take on every value. It must choose from a menu. Just as your favourite cafe may only serve coffee in small, medium, or large, the atom serves energy in discrete sizes, never in between. This discreteness is at the heart of quantum theory. It tells us the world is not infinitely smooth, but pixelated in the tiniest way. Not pixels of light on a screen, but pixels of energy woven into the fabric of matter itself. As you let this thought drift through your mind, notice how the image of steps or a ladder is much gentler than the symbols and equations physicists use on paper. Instead of angular momentum quantization or complicated integrals, you can hold on to the picture of rungs on a staircase, each one stable, each one waiting for an electron to visit. Bohr himself was fascinated not only by the science, but by what it meant for how we think about reality. He famously said that anyone who is not shocked by quantum theory has not understood it, and yet in the quiet way of things, his atom helped build a bridge between the old world of Newton and the new world of probability. It allowed us to imagine atoms not as unstable little solar systems, but as steady, quantized homes for the building blocks of matter. So tonight, as you imagine an electron skipping from rung to rung, or a child stepping down a slide with each step releasing a little sparkle of light, you are touching the heart of Bohr's insight. It is a reminder that the world is both stranger and more structured than it appears, a reminder that stability itself, the reason your body holds together, the reason stars shine steadily in the night sky, depends on the quantized stair-step world of electrons in atoms, and if your eyelids are heavy now, that is perfectly all right. Let the image of glowing colours, of electrons as musicians playing their limited notes, carry you further into rest, because in the gentle framework of quantum theory, even the tiniest steps create the great symphony of existence. There is something comforting about experiments that behave just as you expect. Drop a ball and it falls. Heat water and it boils. Shine light through a glass and it bends. For centuries, this sense of order was the scientist's most reliable friend. But in the early 1900s, new experiments began to play tricks. They seemed to follow rules that were neither classical nor entirely intuitive. Like mischievous actors on a stage, they refused to perform the script that physics had prepared for them. One of the most striking of these was the double-slit experiment. Imagine a simple setup. A wall with two narrow openings, and behind it, a screen to catch whatever passes through. Now picture tossing small marbles at the wall. Some go through the left opening, some through the right, and on the screen you see two neat piles. That makes sense. If you replace marbles with waves on water and let them ripple through two gaps, the ripples overlap and form a striped pattern of peaks and valleys, bright bands and dark gaps. That too makes sense. But what happens when you send particles of light, one by one, through the two slits? At first, you might expect to see two piles like with marbles, but instead something astonishing appears. Over time, as more photons land, they create a pattern of stripes, the same interference pattern you would expect from waves. Even when fired individually, as though the universe were rolling one marble at a time, the photons act as if each one is interfering with itself, as if, in some quiet way, it travelled through both slits at once. This experiment unsettled even the most seasoned scientists. It was as though reality hesitated, unwilling to choose a single path until forced. And indeed, when detectors were placed at the slits to watch which path a photon took, the interference vanished. Suddenly, the particles behaved like marbles again. Simply trying to find out which way they travelled made the wave-like pattern dissolve. It was as if nature whispered, "If you ask me to reveal the path, I will, but if you don't ask, I will wander in both directions at once." The double-slit experiment is not just a laboratory curiosity. It is a window into the heart of quantum mechanics, showing how observation itself changes the outcome. Not observation in the sense of human consciousness, but any interaction that forces the system to choose. It is as though the act of measuring closes a door, while leaving it alone allows all doors to remain open. Another curious experiment was the Stern-Gerlach demonstration, carried out in 1922. Two scientists, Otto Stern and Walter Gerlach, sent a beam of silver atoms through a magnetic field, expecting the atoms' tiny magnetic moments to spread smoothly across the screen, like a mist of grey dots. Instead, the beam split cleanly into two spots. No smear, no continuum, just two sharp outcomes. This revealed that the atom's property, later called spin, was quantized. Not infinite shades, but two distinct choices, like an invisible coin always landing only heads or tails, never sideways. This was another reminder that the quantum world does not allow unlimited options. It restricts outcomes to discrete, step-like values. The everyday analogy might be a light switch. You can flip it on or off, but you cannot freeze it permanently in between. The Stern-Gerlach experiment showed that even microscopic particles live by such rules. Together, these experiments painted a new picture of matter and light. The double slit suggested that particles exist in superpositions, travelling many paths until forced to commit. The Stern-Gerlach experiment showed that fundamental properties are not continuous, but quantized. And when you added Bohr's model of the atom, you could see how these threads wove together. Electrons existing on quantized steps, light acting as both wave and particle, and measurement itself playing a decisive role in shaping outcomes. For the physicists of the early 20th century, these were not comfortable results. Imagine believing that physics is a tidy book, only to discover entire chapters where the words rearrange themselves depending on who is reading. Some researchers argued fiercely about what these results meant. Niels Bohr suggested that we should stop asking what particles really are when unobserved, and instead focus only on the results of measurements. Others, like Albert Einstein, were deeply dissatisfied, insisting that reality must have a deeper explanation, hidden variables waiting to be uncovered. Their debates, spirited and sometimes sharp, would echo across decades, and yet in the laboratory, the results were undeniable. Every time, photons built an interference pattern when unobserved. Every time, the pattern vanished when paths were measured. Every time, silver atoms split neatly into two spots instead of a blur. Physics was being pushed into a realm where certainty gave way to probability, where questions shaped answers, and where intuition had to bend. For us, listening quietly now, These results carry a kind of poetic resonance. Imagine a coin spinning endlessly in the air, existing in all states at once until it lands. Or imagine a violin string vibrating with many notes simultaneously, yet producing only one when touched. These are not perfect metaphors, but they are enough to soften the edges of quantum strangeness into something you can hold gently in your mind. It is often said that the quantum world is weird, but perhaps it is not so much weird as it is delicate. Like frost patterns on a window that vanish when breathed upon, quantum effects reveal themselves only when left undisturbed. The moment we press too firmly, they retreat into classical outcomes. This delicacy is why experiments must be carefully arranged, why quantum computers struggle with noise, and why the universe at our scale feels solid and predictable. As you drift further into this story, notice how these experiments form stepping stones. Planck's quanta opened the door, Einstein's photons walked through it, Bohr's atom gave structure, and the double-slit and Stern-Gerlach experiments pulled back the curtain to reveal the stage. Each piece builds on the last, a quiet rhythm leading us deeper into the mysteries of the quantum. So if your mind feels heavy, with images of marbles and ripples, coins and violin strings, let it rest. The experiments are not meant to be puzzles you must solve tonight. They are lullabies from nature, each humming the same refrain, that reality, at its core, holds possibilities as well as outcomes, and that our attempts to peak shape what we find. Close your eyes, if you'd like, and imagine walking into a room where the air is filled with mist. It swirls gently, curling into corners, thicker in some places, thinner in others. If I asked you where a tiny marble might be hiding in that room, you couldn't point to a single spot. But you could look at the mist and say, it's more likely here, less likely there. That mist is a simple way to picture one of the most important and elusive ideas in quantum physics, the wave function. When scientists first tried to make sense of atoms, they needed more than Bohr's stair-step orbits. They needed a way to describe how electrons behave not just as particles, not just as waves, but as something in between, a shimmering in between that doesn't fit neatly into either box. Enter Erwin Schrödinger in 1926, with what became known as the Schrödinger equation. If you picture Newton's laws as recipes for predicting how an apple will fall, Schrödinger's equation is a recipe for predicting probabilities. It doesn't tell you where the electron will be, but it tells you how likely you are to find it here or there. Instead of saying the electron is at this point, it paints a cloud, a haze of possibilities. In symbols, physicists write it with the Greek letter Psi, but rather than saying psi, let's think of it as the probability mist, the fog that tells you where nature is inclined to reveal the particle. The thicker the mist in a region, the more likely the electron will appear there if you look. One of the most beautiful outcomes of this idea is seen in the hydrogen atom, the simplest atom of all. If you take Schrödinger's recipe and apply it to hydrogen, a single electron orbiting a single proton, you don't get neat circles, like planets. Instead, you get shapes, delicate patterns of probability that physicists call orbitals. These orbitals are like standing waves, resonant forms where the electron's probability cloud gathers and settles. Some are spherical, like tiny soap bubbles around the nucleus. Others have lobes, almost like petals on a flower. Imagine dropping a marble into a vibrating bowl of jelly. The ripples settle into patterns, regions where the jelly swells and regions where it quiets. Hydrogen orbitals are like those patterns, except they are made not of jelly but of probability itself. The electron is not buzzing around like a little moon. It is spread out, smeared into a standing wave of chance. It is tempting to ask, but where is the electron really? Quantum physics answers in a way that can feel unsettling. It isn't anywhere in particular until you measure it. Before that, it lives in its wave function, a state of possibility. The mist fills the room, waiting, and only when you look does the marble condense into one corner. This is why scientists sometimes say the wave function is the most complete description of a quantum system. It carries all the information about what could happen, but none about what will happen until measured. Think of it like a weather forecast. The forecast might say, there is a 60% chance of rain. That doesn't mean it is raining yet, or that it won't rain. It means the possibilities are weighed, and only when the day unfolds do you see the outcome. The wave function is like that forecast, but for every aspect of a quantum system: position, energy, spin. It holds the entire spread of potential futures. The leap here is subtle. In the classical world, uncertainty comes from our lack of knowledge. If you don't know where a coin fell under the couch, that's ignorance, not reality itself being fuzzy. But in the quantum world, uncertainty is baked into nature. It isn't that the electron has a secret address and we haven't looked hard enough. It's that the electron genuinely does not have a fixed position until the mist is forced to collapse into one. This mist metaphor also explains why atoms are stable. Remember how Bohr showed that electrons only live on certain rungs of the energy ladder? Schrödinger's equation deepened that picture. The electron's wave function forms standing patterns that cannot simply shrink to nothing. These waves can only exist in specific forms, just as a guitar string can only play certain notes when plucked. The allowed orbitals are like harmonies, and the atom is the instrument playing them. There is another poetic way to hold this in your mind. Picture a lantern illuminating fog in the forest at night. You see beams spreading, patches glowing, shapes appearing. The fog is not solid, but it gives form to what otherwise would be invisible. The wave function is like that illuminated fog, revealing where a particle is likely to emerge, even if the particle itself is hidden until you step closer. And though this may sound abstract, the fingerprints of wave functions are all around you. The colours of chemicals, the glow of neon signs, even the shape of molecules in your body, all depend on the specific forms of electron clouds. If electrons really orbited like planets, chemistry would be impossibly bland. Instead, because electrons inhabit these strange, misty orbitals, atoms can bond in countless ways, weaving the complexity of life. For Schrödinger himself, this was both triumph and torment. His equation worked brilliantly, predicting experiments with uncanny accuracy. Yet what did it mean? Was the wave function real, a physical mist surrounding the nucleus, or was it just a mathematical tool? This question remains alive even today. Some physicists say the wave function is the most real thing we can talk about. Others say it is merely a way to encode our knowledge, not a tangible cloud, but a story we tell to make sense of outcomes. As you let your thoughts drift, you don't need to resolve this debate. It is enough to imagine the wave function as a gentle haze, thicker here, thinner there, offering probability instead of certainty. It is a reminder that not everything must be sharply defined to be meaningful. Sometimes, the very blur, the openness of possibility, is what makes the world stable and alive. And so, as you breathe slowly, picture a quiet hydrogen atom, one proton at the centre, and an electrons cloud shimmering softly around it. No planets racing in circles, no collapse, just a standing mist of chance, humming gently in the dark. In that mist lies both mystery and order, and perhaps a bit of comfort too, because it shows us that even at the smallest scales, the universe has patterns, rhythms, and harmonies, even if they are written in the language of probability. If you've ever watched a coin spin on a tabletop, you know the strange tension of possibility. For a moment, it is neither heads nor tails, but a blur of both. Then, with a gentle clink, it lands, and one outcome becomes real. The quantum world lives in that blur, in superpositions where many futures are layered together. But unlike the coin, which we can imagine as secretly tilting toward one side even while it spins, the quantum version is more radical. Until you look, it truly holds both options. And when you do look, the wave function, that mist of probabilities we spoke about before, collapses into a single outcome. This process is what physicists call measurement. But here, the word carries more weight than when we measure a table with a ruler or weigh flour in a kitchen. Measurement in quantum mechanics does not just reveal what was already there, it changes the state itself. The mist condenses, the spread of possibilities shrinks, and one reality is chosen. To make this vivid, Erwin Schrödinger, the same scientist who gave us the equation for the wave function, created a thought experiment in 1935. He asked us to imagine a cat placed inside a sealed box, along with a tiny amount of radioactive material, a detector, and a vial of poison. If the radioactive atom decays, the detector notices, and the vial breaks, releasing the poison. If the atom does not decay, the cat remains safe. According to quantum rules, before you open the box, the atom exists in both states, decayed and not decayed. That means the cat, tied to the atom's fate, is both alive and dead at the same time. Of course, no real cat was harmed in Schrödinger's thought experiment. His point was to highlight the tension between the microscopic and the macroscopic worlds. At the atomic scale, superpositions are natural, electrons happily existing in many places at once. But at the scale of cats, or people, or teacups, we never see this. Cats are either alive or not, never both. So where does the transition happen? When does the mist of probabilities give way to the solid world we know? Some scientists say that collapse happens whenever a system interacts with the environment, when it becomes entangled with something large enough that the superposition dissolves into ordinary outcomes. Others emphasize the role of observation, suggesting that it is our act of asking, our choice to measure, that forces the decision. The truth is still debated. What matters for us, as we wander gently through the quantum landscape, is the image itself, the mist shrinking into one outcome when pressed. Let's soften this with an everyday example. Imagine you're baking bread and you've left it in the oven. Until you open the door, the loaf could be perfectly risen, slightly underdone, or even a little burnt. All possibilities exist in your imagination. The moment you check, you know. The uncertainty collapses into one loaf, one reality. The bread, of course, was always in one state. But in the quantum world, before you open the oven, the bread really does exist in overlapping maybes. Only when you peek do you find out which one is real. This is why the language of collapse is so compelling. It feels less like flipping through pages of a book and more like writing the sentence as you read it. Each measurement completes the story, turning the potential into the actual. There is a gentle irony here. Our everyday world feels solid because we are constantly surrounded by interactions that collapse possibilities into outcomes. Photons of light bouncing off a chair collapse its position into something definite for your eyes to see. Molecules of air brushing against your skin collapse the warmth you feel into one stable value. The world is constantly measured by its own environment, long before our minds take notice. Schrödinger's cat continues to haunt physics classrooms and late-night conversations. Is the cat really both alive and dead before we look? Or is it only our description that carries the blur? Some interpretations of quantum mechanics say the collapse is a fundamental physical process, nature's way of deciding. Others say the wave function never collapses at all. It only appears that way because the universe branches into parallel realities. In one, the cat lives. In another, it does not. And in still others, new interpretations suggest collapse is only about our knowledge, not about reality itself. We don't need to solve these debates tonight. What matters is the gentle truth they all circle around. In the quantum world, outcomes do not exist until something forces them to. The act of looking is not passive. It is part of the story, part of the fabric of reality. You can think of it like a lantern shining into fog. Before the light, the fog is everywhere, spreading without shape. When the lantern shines, the beam defines a path, a slice of visibility. In that moment, One part of the fog becomes the world you can see. The rest fades into darkness. The lantern is measurement. The fog is the wave function. The clear path is the collapsed outcome. This way of seeing brings a kind of humility. It tells us that the world is not fully formed, waiting quietly with all details in place. Instead, it is pliable, flexible, a realm of maybes that solidify only when touched. Far from making reality less real, this makes it more alive, always in the act of becoming. So, as you lie here listening, imagine a coin spinning softly, never landing until you glance. Imagine a cat in a box, safe and unsafe in overlapping possibilities. Imagine a loaf of bread both risen and fallen, waiting for your hand to open the oven door. These are not riddles to frustrate you, but gentle reminders that reality is deeper and stranger than it seems. And in that strangeness, there is wonder. And if your eyes grow heavy now, let them close. Collapse, after all, is not only for electrons, it is for thoughts too, which fade into one dream as you drift to sleep. There's a familiar comfort in being able to say, I know where it is, and I know how fast it's moving. It's the way we navigate every day. If you're driving, you know the car is on the road and you know the speed on the dashboard. If you toss a ball to a friend, you can trace its arc and be confident where it will land. In the classical world, this combination of position and momentum feels natural, almost obvious. But in the quantum world, even this most basic certainty dissolves. Werner Heisenberg, one of the pioneers of the new physics, discovered in 1927 that you cannot know both where something is and how fast it's moving with unlimited precision. The sharper you make one picture, the blurrier the other becomes. This is not a matter of faulty instruments or poor eyesight. It is woven into the structure of nature itself. Heisenberg's insight came to be known as the uncertainty principle. Though the word uncertainty can sound like doubt, here it is not about human ignorance. It is about reality's own boundaries. At the smallest scales, particles refuse to give us both pieces of information at once. Imagine trying to photograph a hummingbird in flight. If you use a very fast shutter speed, you freeze the bird's wings, capturing its position clearly in midair. But the motion becomes hidden. You can't see how fast the wings are beating. If you use a slower shutter speed, you capture the blur of motion, the rhythm of the beating wings, but the position of each feather is lost. The more you sharpen one side of the story, the more the other side slips away. In the quantum world, this is not just a matter of camera choice, it is fundamental. Electrons, for example, are described by wave functions, those misty probability clouds. A tightly squeezed wave function, which pins down position more sharply, spreads widely in momentum. It's like pulling a blanket tight in one direction, only to have it stretch and loosen in another. The universe insists that there is always a trade-off. This principle has a surprising gift. It explains why atoms are stable. If electrons were tiny marbles circling a nucleus, nothing would prevent them from tumbling inward and collapsing into it. But the uncertainty principle prevents such a fate. To confine an electron too tightly, to force it into a tiny box at the nucleus, would make its momentum wildly uncertain. It would dart away with tremendous energy. So instead, the electron hovers as a cloud around the nucleus, balanced by the uncertainty itself. Stability, at the atomic scale, is born from fuzziness. Think of it like trying to confine a restless cat in a small box. The smaller the box, the more frantically it scratches and pushes. Give it a bit more space and it calms into a steady presence. In this playful metaphor, the uncertainty principle is the reason atoms, and therefore everything in your world, can calmly exist without imploding. Another way to picture this is with music. A sharp, perfect note from a tuning fork has no rhythm or beat. It is pure tone but stretched infinitely in time. A short drum beat, on the other hand, is precise in time but spreads into many frequencies, a whole mix of tones. You cannot have both perfect timing and perfect pitch in the same sound. The act of sharpening one sacrifices the other. In physics, position and momentum dance to this same rule. It's tempting to think this principle only applies to tiny particles, but in truth, it underlies everything. We don't notice it in daily life because the uncertainties at large scales are vanishingly small. The blur of your coffee cup's position and momentum is so tiny that it never enters your awareness. But in the realm of atoms and electrons, this blur is not a footnote. It is the story itself. Heisenberg's principle also reminds us of humility. Classical physics once promised a perfect clockwork universe. If you knew everything now, you could predict everything forever. Quantum physics tells us there are limits, not just to what we know, but to what can be known. The universe keeps some of its cards hidden, not out of secrecy, but because reality itself is not written in sharp ink. It is painted in soft strokes. Even Einstein struggled with this idea. He famously said he could not believe that God plays dice with the universe. He longed for a deeper order where certainty would be restored. But time and again, experiments proved that the uncertainty principle is not an inconvenience to be patched over. It is a cornerstone of how the world works. And so, as you lie listening, you might imagine reality not as a hard grid but as a watercolour painting. Edges blur into one another, shapes overlap, and yet the picture is still whole, still beautiful. Certainty gives way to possibility, and in that openness lies the resilience of the universe itself. Perhaps the most gentle takeaway is this: uncertainty is not chaos, it is balance. It is the reason atoms endure, the reason stars shine, the reason your body holds together as you breathe. Without it, everything would collapse. With it, the universe has room to be. So let your thoughts settle like mist. If they blur at the edges, that is all right. The uncertainty principle teaches us that clarity in one place always comes with softness in another. And sometimes, that softness is exactly what allows us to rest. Picture an orchestra warming up before a concert. Each instrument plays a different note, violins sliding upward, flutes trilling, drums rumbling softly. For a moment all the sounds overlap, not yet chosen into melody. That rich, tangled hum is a simple way to think about one of the most unusual features of the quantum world: superposition. In classical life, a thing is one way or another. A light switch is on or off. A cat is asleep or awake. A coin is heads or tails. But in quantum mechanics, particles can exist in layered possibilities. An electron can be here and there. A photon of light can be polarized this way and that way. It isn't indecision. It is the rule of the universe at small scales. Until something interacts with the system, until there is a measurement, the quantum object holds many maybes at once. This is more than metaphor. It is what experiments show over and over. Send photons through a polarizing filter, and they emerge in states that are neither purely vertical nor purely horizontal, but in a superposition, both orientations coexisting until measured. Electrons confined in atoms spread out in overlapping clouds, each possible orbital layered into the wave function. Even whole molecules carefully shielded from disturbance have been placed into superpositions, existing in two paths at once like a traveller walking down both sides of the street. It can feel impossible to picture. But try this. Imagine holding a deck of cards face down. The top card could be a king, a queen, or any other card. Before you flip it over, all those possibilities exist in the game. In classical thinking, the card has a fixed identity. You simply don't know it yet. In quantum thinking, the card is genuinely all options layered together. Only when you flip it does the deck collapse into one story. The difference is subtle, but profound. Classical ignorance is like not peeking. Quantum superposition is like having the deck shuffled into every card at once, a shimmering overlap of futures. Why should nature behave this way? One reason may be that particles are not tiny billiard balls, but excitations of underlying waves. and waves naturally overlap. Two ripples in water can pass through each other, creating patterns that vanish as quickly as they form. Superposition is simply the mathematics of overlapping applied to the deepest layers of reality. And yet, fragile as it sounds, this feature of quantum mechanics is not just philosophical curiosity, it is the foundation of the emerging field of quantum technology. Quantum computers, for example, exploit superposition to explore many possible solutions at once. Where a classical bit in your laptop is either 0 or 1, a quantum bit, or qubit, can be both 0 and 1 at the same time. Multiply that by many qubits, and you have a system exploring an astronomical number of pathways simultaneously. Imagine trying to find your way out of a vast maze. A classical computer walks each corridor, testing each path one by one. A quantum computer, in principle, can drift like mist through all corridors at once, sensing where the exit lies. When the final measurement is made, the system collapses into the correct solution. Of course, in practice it is far more delicate, but the metaphor shows why superposition is so powerful. In everyday life, we rarely encounter this. A chair is not in superposition of being in the kitchen and the living room. Your keys are not both lost and found until you check. The reason is that superpositions are extraordinarily fragile. The environment, air molecules, photons, vibrations, constantly interacts with objects, collapsing their many maybes into single realities. We call this fragility decoherence, and it explains why the quantum world feels so different from the classical one. Superpositions vanish quickly in our noisy surroundings, surviving only in carefully protected experiments. But for a moment, as you listen, allow yourself to imagine a world where superposition is obvious. Imagine flipping a coin and seeing it hover as both heads and tails, shimmering between outcomes. Imagine standing at a fork in the road and walking down both paths at once, only to discover, when you look back, that you chose one. Imagine holding a glass of water that is both full and empty until you sip. These pictures sound dreamlike, and perhaps that's the best way to hold them. Superposition is less about physical intuition, and more about accepting that reality is richer than our common categories. Like a symphony not yet played, it holds many melodies, and only when the conductor's baton falls does one line emerge. For us, the beauty lies not just in the strangeness, but in the reminder that possibility itself is part of the fabric of the world. Superpositions show that the universe does not rush to make decisions. It holds options gently, like mist lingering before the sun. So as you rest, picture that orchestra tuning in the half-light, each note a possibility, none yet chosen. Picture a card deck shimmering with every face at once. Picture yourself drifting down both paths of a road. These are not puzzles to strain over, but lullabies of chance, humming that the world itself lives in many maybes before it settles into one. And if your eyes close now, let them. Your dreams too are superpositions, images and stories layered until the morning chooses which to remember. If you hold a soap bubble in your hands, you know how delicate it is. The colours shimmer, thin layers of possibility ripple across its surface, and with the lightest touch it can pop. That fragility is a good way to think about what scientists try to do when they take the strange principle of superposition and turn it into something useful. Out of the dreamlike behaviour of particles existing in many maybes at once, they build qubits, the basic units of quantum computers. In your everyday devices, information is stored in bits, tiny on-off switches made of transistors. A bit is either 0 or 1, like a light switch flipped down or up. Billions of these bits work together to stream a movie, display a message, or run a program. The world of classical computing is built on this clarity. But a qubit, a quantum bit, is different. It can be 0 and 1 together, a layered superposition that only collapses to one outcome when measured. Imagine tossing a coin into the air and holding it there forever, spinning. While it spins, it embodies both possibilities at once. That hovering state is the essence of a qubit. Instead of walking down one corridor of the maze as a classical bit must, a qubit drifts through both. Instead of choosing a single note, it hums in harmony, carrying chords of possibility. This is why people say quantum computers have extraordinary potential. A few qubits, entangled and superposed, can represent far more information than the same number of classical bits. Where ordinary computers explore solutions step by step, quantum systems can explore many at once, like mist seeping through every corner of a labyrinth simultaneously. But if this sounds like a dream, it is because building such systems is very much like trying to balance soap bubbles. The very same delicacy that makes superposition so fascinating also makes it fragile. The moment a qubit interacts with its environment, a stray photon, a vibration, a trace of heat, the superposition collapses. This process is called decoherence, and it is the constant enemy of quantum technology. Picture trying to carry a tray full of teacups across a crowded room. Each cup is balanced, filled to the brim. The slightest jostle, a bump from someone's elbow, and the tea spills. Decoherence is that bump, the interruption that destroys the delicate balance of the qubits. To keep them coherent, scientists must shield their systems with extraordinary care. Ultra-cold temperatures, near-perfect vacuums, and layers of protection from outside noise. Even with all this, errors creep in. Qubits are notoriously finicky, sometimes flipping unpredictably or losing their alignment with one another. To cope, researchers develop elaborate methods of quantum error correction, weaving many fragile qubits together into patterns that can survive mistakes. It is as though a choir of voices sings together, so that even if one falters, the harmony continues. Despite these challenges, real quantum processors already exist. They are small, with just a handful of qubits compared to the billions of bits in your phone. But they demonstrate that superposition and entanglement can be harnessed, not just imagined. Some are made of superconducting circuits, loops of metal cooled to near absolute zero, where electrical resistance vanishes. Others trap individual ions, floating in electromagnetic fields, their internal states serving as qubits. Still others use photons, the particles of light, as carriers of quantum information. Each approach is like a different instrument, all attempting to play the same fragile tune. Why go to such lengths? Because certain problems are naturally suited to quantum advantage. For example, simulating the behavior of molecules, a task that grows impossibly complex for classical computers, may be handled elegantly by quantum ones. Chemistry, drug design, material science, and optimization problems could all change once larger, reliable quantum systems are built. Think of it as trying to read a library of books. A classical computer can only open one at a time, scanning each page. A quantum computer, in principle, can open many at once, holding their stories simultaneously until the final answer emerges. This is not magic. It is the mathematics of superposition at work, carefully shepherded by scientists into practical form. And yet, even the most optimistic researchers remind us, this technology is still young. We live in what is called the Renanesque era, short for noisy intermediate scale quantum. The word noisy here is not about sound, but about interference, the unavoidable disturbances that still plague qubits. Today's machines are small, experimental, and prone to errors. They are like the first airplanes, fragile, wobbly, barely able to fly, yet full of promise for what might one day be possible. There is a gentle lesson in this fragility. It shows us that progress does not come from eliminating the strangeness of quantum mechanics, but from embracing it. To build a quantum computer, one must learn to work with mist, to guide soap bubbles without popping, them to tune orchestras of possibilities that collapse into single melodies only when the final note is played. And as you rest, You might imagine yourself holding one of these qubits in your hand, a glowing droplet of potential. It is both 0 and 1, both yes and no, both path A and path B. It hums quietly with futures waiting. If you press too hard, it vanishes. If you cradle it softly, it endures just long enough to whisper an answer. Superpositions taught us that particles can hold many maybes. Qubits show us that those maybes can be shaped into tools. It is an ongoing story, one where fragility is not a weakness, but a doorway into new possibilities. And so, like bubbles shimmering in the dark, qubits invite us to see the universe not as rigid and binary, but as flexible and alive with options. Perhaps that is why the idea feels so strangely calming. The world itself, at its core, does not rush to decide. It waits, holding many paths, as if reminding us that we too can rest in uncertainty and still find our way. Imagine 2 dice, freshly carved from the same block of wood. You roll one on your table, and your friend, far away, rolls the other at the exact same time. By chance, sometimes they match, sometimes they don't. That is the way ordinary dice behave. Independent, each one following its own tumble. But in the quantum world, particles can be linked in such a deep way that their outcomes match every time, no matter how far apart they are. This mysterious bond is what we call entanglement. Entanglement begins when 2 particles are created together, often in a single event, like twins born from the same spark. From that instant, their states are intertwined. If one particle is found in one configuration, the other is instantly found in the complementary one. It doesn't matter whether they're a centimetre apart or light years away. Measure one, and the other responds as though it knew the result all along. Albert Einstein famously disliked this. He called it spooky action at a distance, a phrase that captured both his skepticism and his discomfort. For Einstein, the universe should be local. What happens here should not instantly affect what happens over there, especially if over there is on the other side of the galaxy. He believed there must be hidden information, secret instructions carried by the particles that explain the correlation without magic. But decades of experiments have shown otherwise. The connection is real, and it cannot be explained by any simple set of hidden notes. To make sense of this, let's soften it with imagery. Picture 2 dancers on opposite sides of a stage, blindfolded, never able to hear each other. Yet when one raises an arm, the other raises the same arm in perfect synchrony. No signal is sent, no cue exchanged. They simply move as one, connected in a way that transcends the space between them. That is entanglement, a choreography of probability that links particles beyond distance. And the strangeness does not stop there. Entanglement is not just about matching outcomes. It means that the particles cannot be described separately at all. Their shared wave function, their shared mist of possibility, covers both together. You cannot point to one and say, here is particle A, fully described, and here is particle B. You can only describe them as a pair, as one extended system spread across space. This defies our usual language. In our daily world, objects have properties of their own. A cup is hot or cold, a lamp is on or off, a book is open or closed, but entangled particles refuse this individuality. Their identities are blurred into a shared state, and only when measured do they reveal correlated outcomes. It is as if the universe whispers, these two belong to one story. Entanglement also changes how we think about information. Suppose you and a friend each hold one particle of an entangled pair. When you measure yours, you instantly know the result of your friend's, no matter how distant. It's not faster than light communication, no usable message is sent, but it is an eerie echo, a reminder that quantum systems carry a form of wholeness that our intuition struggles to grasp. This wholeness can be harnessed. Quantum key distribution, a method of secure communication, uses entangled particles to ensure that any eavesdropping attempt is immediately detected. Quantum teleportation, another application, allows the state of one particle to be transferred to another at a distance, not by moving the particle itself, but by transferring its information. It is less like beaming people across space, and more like copying the pattern of one candle flame onto another far away, so that the second flame becomes identical to the first. Even more profoundly, entanglement is essential for quantum computing. Qubits entangled with one another are not just independent bubbles of possibility. They are joined into a collective system where outcomes are woven together in complex webs. This is what gives quantum machines their power, the ability to explore patterns of solutions that no classical machine could attempt. It may feel abstract, but let's bring it close with a simple picture. Imagine two coins, one in your pocket and one in your friend's, miles apart. Normally, if you flip both, the results are random. Heads here, tails there, no connection. But if they were quantum entangled, the flips would always match, or always complement each other regardless of distance. And the match would not come from secret marks scratched on the coins beforehand. It would emerge in the moment of measurement, drawn from their shared mist of possibility. The mystery of entanglement has led to endless debates. Is reality non-local, allowing correlations to leap across space instantly? Or does our picture of particles as separate objects need to be abandoned? The details remain deeply technical, but for our quiet journey tonight, it is enough to sit with the image. Two particles, no longer two, moving in harmony across unimaginable distances. There is a kind of comfort in that thought. In a universe that often feels vast and empty, entanglement is a reminder of connection. It shows us that separation is not always as absolute as it seems. Beneath the stars, even across galaxies, there are threads of probability weaving things together. So, as you breathe slowly now, imagine two tiny sparks born from one flame, drifting apart into the night. However far they go, they remain linked, their fates written not separately but as one. That is entanglement, a tale of two particles, and perhaps a gentle reminder that in some hidden way, we are all part of a shared wave function too. When Albert Einstein complained about spooky action at distance, many scientists shared his unease. The idea that particles could influence each other instantly, no matter how far apart, felt like it violated common sense. Surely, they thought, there must be hidden instructions built into each particle at the moment they were created, secret notes tucked into their pockets, so that when one is measured, it only looks as if the other responds. The reality would be classical underneath, neat and tidy. For decades, this question hung in the air like an unresolved chord. Then, in the 1960s, a quiet breakthrough came from a physicist named John Bell. Bell realised the debate could be tested. He derived what came to be known as Bell's inequalities, not as complicated equations to be memorised, but as a set of limits on how strongly two particles could correlate if they were only following hidden instructions. If experiments found correlations stronger than these limits, then no hidden variables could explain them. The universe itself would have to be non-local in some sense, holding connections beyond classical rules. Think of it like two students sitting apart during a test. If they each received hidden notes in advance, you'd expect their answers to match in a certain predictable way. Bell's inequalities set the boundaries for how good their agreement could be if all they had were those notes. But if their answers matched even more strongly than the boundaries allowed, then something else must be happening. Some invisible connection keeping them in sync during the test itself. In the 1970s and 80s, experiments began to probe this question with light particles, or photons. Scientists created pairs of entangled photons and measured their polarizations at distant detectors. Again and again, the results violated Bell's limits. The photons' responses were too strongly correlated to be explained by any secret notes written at the start. It was as if the universe itself refused to be boxed into classical rules. At first, skeptics pointed out possible loopholes. Maybe the detectors were flawed. Maybe the sample. size was too small, or maybe some subtle communication leaked between the particles. Over time, researchers closed each loophole one by one. They spread the detectors miles apart so no signal could pass between them quickly enough. They randomized the settings at the last instant so the particles could not have prepared a script. By the early 2000s, the evidence had become overwhelming. Entanglement correlations really do surpass classical limits. The quantum world does not run on hidden instructions. What does this mean in plain terms? It means that entangled particles are not separate objects carrying private identities. They are one shared system, described by a single wave function, no matter how far apart they are placed. Measuring one does not send a signal to the other. Instead, the two outcomes emerge from the same whole, like two hands of a single body moving in rhythm. This has deep implications. It tells us that the universe is not assembled from tiny independent parts, but from webs of connection. The boundaries we draw between objects are sometimes less fundamental than we think. At the quantum level, wholeness comes first, separation second. And it isn't just philosophy. The practical uses of these insights are already appearing. Quantum cryptography, for example, uses entanglement to guarantee secure communication. Two parties share entangled particles. If anyone tries to eavesdrop, the disturbance breaks the correlations, and the intrusion is immediately noticed. It is like two friends exchanging secret handshakes that no outsider can imitate. Quantum teleportation, another application, transfers the state of one particle onto another at a distance. Nothing physical travels between them. No particle flies across space. Instead, information is reassembled in the partner particle through entanglement. Imagine copying the precise flicker of one candle flame onto another far away, until the second flame is indistinguishable from the first. The flame itself does not move, but its pattern does. Even quantum computing relies on this. Entangled qubits are not separate on-off switches, but threads in a single fabric. Calculations are woven through these threads, creating outcomes that depend on the correlations among all of them together. It is not one bit following another, but many voices singing in harmony, their strength coming from the very connections Einstein once doubted. Bell's theorem, though expressed in mathematical language in physics journals, carries a simple message for us tonight. The universe is stranger, more connected than even Einstein dared imagine, and the experiments prove it. No hidden notes, no tidy classical instructions. Instead, a reality where particles dance together across distance, their steps guided by a shared score we're only beginning to hear. There is something calming in this. It tells us that separation is not the only truth. Beneath the vastness of space, beneath the loneliness we sometimes feel under the stars, there are bonds that defy distance. Two photons born together can remain connected across miles. Two particles can be woven into one story. Perhaps, in its own quiet way, this speaks to us too, that we are not quite as separate as we often believe. So as you rest now, imagine two dice rolled on opposite ends of the earth, always matching beyond chance. Imagine two candle flames flickering the same way, though one is here and one is galaxies away. Imagine invisible threads tying sparks of light into one tapestry. That is Bell's gift, not just a theorem, but an invitation to wonder at how deeply the world is stitched together. Imagine rolling a ball up a hill. If you don't push hard enough, the ball rolls back down. It never magically appears on the other side because in the everyday world, energy rules are strict. To cross the hill, you need enough momentum to climb over the top. But in the quantum world, rules bend in unexpected ways. A particle does not live at a single point with a single path. It is described by its wave function, that mist of probabilities we've spoken about. And that mist doesn't stop abruptly at barriers. It seeps a little way into them, like fog curling around a wall or light shining faintly through curtains. Most of the mist bounces back, but a delicate tail continues beyond the barrier. If the barrier is thin enough, the particle has a chance, not a certainty, but a chance, of appearing on the other side without ever climbing over. This is quantum tunneling, the ability of particles to slip through barriers they seemingly should not cross. It is as if the ball you rolled at the hill sometimes reappeared on the far side, not by climbing, but by tunneling quietly through. For scientists, this is not just poetic fancy. It is something measured and relied upon. In fact, without tunneling, the sun itself would not shine. The heart of a star is a furnace where hydrogen nuclei collide and fuse into helium, releasing the light that warms our days. By classical physics, these collisions should be impossibly rare, because the nuclei are both positively charged and repel each other strongly. The repulsion is like a high hill, far too steep for the nuclei to climb at the temperatures inside stars, and yet stars burn steadily for billions of years. They do so because quantum tunneling lets the nuclei slip through the barrier of repulsion, just often enough to keep fusion going. Each sunrise you see is powered by particles tunneling through impossible hills in the sun's core. On Earth, tunneling also explains radioactivity. In alpha decay, for example, a heavy nucleus emits a small cluster of particles. Classically, those particles are trapped by the nuclear forces, like marbles stuck inside a bowl with walls too high to escape. But their wave functions extend beyond the barrier. Every so often the mist leaks through, and the particles emerge on the outside, as if the walls had briefly become transparent. The steady ticking of a Geiger counter used to measure radioactivity is the sound of tunneling in action. And tunneling is not limited to nature's distant stars or radioactive rocks. It powers technologies we use every day. Consider the scanning tunneling microscope, an instrument invented in the 1980s. It works by placing a sharp metal tip extremely close to a surface, so close that electrons can tunnel across the tiny gap between tip and sample. By measuring the tunneling current, scientists can map surfaces atom by atom. It was the first tool that allowed us to see individual atoms directly, not just infer them. The pictures it produced, tiny rows of atoms lined like beads, clusters forming nanostructures, were a triumph, showing us the quantum world with astonishing clarity. Tunneling also underlies tunnel diodes, electronic components that rely on the ability of electrons to slip through barriers. These devices switch quickly and efficiently, useful in high-speed circuits, and in modern flash memory, the technology that lets your phone and computer store data, electrons tunnel through insulating layers to trap or release charge. Each time you save a picture or a note, tunneling plays its invisible part. To anchor the idea in daily imagination, think again of the ball and the hill. Most of the time the ball rolls back, but if you watch long enough there's a tiny chance that the ball simply appears on the other side. Or picture yourself standing at a locked door. In the classical world, without a key, you cannot enter. In the quantum world, there's always a faint chance you find yourself on the other side anyway, as if the lock had briefly lost interest in holding you back. This doesn't mean tunneling is magic. The probabilities are dictated by the thickness and height of the barrier. A very wide hill makes tunneling almost impossible. A thinner one increases the chance. The rules are precise, but they belong to the quantum world of probabilities, not to the classical certainty of marbles and ramps. Heisenberg's uncertainty principle plays a role here too, because particles cannot have both their position and momentum pinned down exactly. Their probability clouds extend into places that look forbidden. The fuzziness of their nature makes the impossible possible, at least occasionally. What's remarkable is how natural this becomes once you accept it. For the quantum world, tunneling is no stranger than reflection or refraction. It is simply part of the vocabulary of matter, one of the ways particles explore space. For us it remains astonishing because it contradicts everyday logic. Yet without it, stars would not shine, life would not exist, and technology would be poorer by many tools. As you let this thought settle, notice how tunneling offers a comforting metaphor. Barriers that seem impassable are sometimes not absolute. Possibilities exist beyond what looks like the limit. The world, at its most fundamental level, is not built from rigid walls, but from soft probabilities that sometimes allow for surprise. So as you rest, imagine a ball gently appearing on the far side of a hill, a faint whisper of chance carrying it through. Imagine the sun overhead, burning because particles in its core slip through barriers that should hold them. Imagine your computer or phone, quietly storing memories thanks to electrons tunneling across tiny distances. These are not exotic exceptions, but everyday expressions of the quantum. Perhaps that is the lesson tunneling leaves us with, that even walls are not final, that even limits are sometimes porous, and if the universe itself allows for such quiet miracles, maybe we too can hold the possibility of slipping through our own invisible barriers, finding ourselves on the far side of doubt, of worry, of restlessness, where calm awaits. If you close your eyes and picture empty space, what comes to mind? Perhaps a dark void, still and silent, without sound, without air, without even a speck of dust. It seems natural to imagine nothingness as truly nothing. Yet quantum physics tells a different story. What we call empty space is not a lifeless void at all, but a restless sea, humming with activity that never quite stops. This idea is one of the strangest gifts of quantum theory, the realization that the vacuum, space stripped of matter, light, and energy, is never truly empty. Even in perfect darkness, fluctuations stir. Particles flicker in and out of existence, borrowing energy for a fleeting instant before disappearing again. The vacuum is more like an ocean whose waves are too small for the eye to see, yet whose ripples shape the world. To soften this into something familiar, imagine walking into a room that looks empty. No furniture, no people, bare walls. You stand still, thinking the space is silent. Then you notice the faint hum of a refrigerator in the next apartment, the creak of pipes, the whisper of air moving through unseen cracks. It is not truly silent. The vacuum of space is like that. What looks empty carries hidden whispers. One way this hidden activity reveals itself is through the Casimir effect, named after the Dutch physicist Hendrik Casimir. Imagine placing two uncharged metal plates very close together in an otherwise empty vacuum. Classical physics predicts nothing should happen, but in reality, the plates are gently pulled together, as though an invisible hand is pressing them inward. The force comes from the quantum fluctuations of the vacuum itself. The restless mist of possible particles is slightly different between the plates than outside them, and that imbalance nudges the plates together. It is a tiny effect, but measurable, and it proves that even emptiness has energy. Another way to picture it is to think of silence in music. Even in pauses, there is tension, a sense of notes waiting to be played. The vacuum is that pause, not dead, but full of potential vibrations. The Casimir plates feel the pull of those silent notes, a reminder that nothingness is never as simple as it seems. These fluctuations also tie into one of the great mysteries of modern physics, dark energy. Astronomers have discovered that the expansion of the universe is speeding up, as though some hidden energy is woven into the fabric of space itself, pushing galaxies apart. Quantum theory suggests that the restless vacuum carries enormous energy, far more than we observe. Reconciling the two is one of the deepest puzzles in science today. How can the vacuum be both wildly energetic in theory and yet so subtle in practice? The answer remains out of reach, like a secret hidden in plain sight. Closer to home, the restless vacuum plays roles in particle physics. In the framework known as quantum field theory, every particle is seen as a ripple of an underlying field that stretches across all of space. The vacuum is not the absence of these fields, but their lowest energy state still alive with fluctuations. Picture a still pond. Even on the calmest day, tiny ripples dance across the surface. The vacuum is that pond never fully flat. And these ripples are not meaningless. They can affect the properties of particles themselves. For example, electrons interact with the sea of fluctuations, their apparent mass and charge shaped by the vacuum. It is as though the electron is never truly alone, always accompanied by a shimmering crowd of ghostly companions from the vacuum around it. The restless vacuum is not only a scientific concept but also a poetic one. It reminds us that silence is never empty, that stillness is alive with hidden motion. Think of sitting in a quiet forest at night. At first it feels utterly calm, then your ears begin to pick up faint sounds, a rustle of leaves, the distant call of an owl, the movement of small creatures unseen. Emptiness reveals itself as fullness once you listen closely. For sleep, this thought can be strangely comforting. If even the void between stars is alive with hidden whispers, then perhaps emptiness in our own lives is not so barren either. A pause in conversation, a quiet night, even the moments before dreams arrive, all of them may be filled with unseen potential, waiting to stir. The Casimir effect may be a laboratory curiosity, but it carries this deeper meaning. Two plates placed close together feel the invisible pressure of the restless vacuum. You too may feel the gentle pressure of possibilities even in stillness. What looks empty may be the most alive of all. So as you rest now, imagine the space around you not as silence, but as a soft ocean of fluctuations. Imagine the air in the room humming faintly with possibilities, too small to notice, yet always present. Imagine the universe itself expanding, carried by this hidden energy of the vacuum. It is not a frightening thought, but a quiet one. Emptiness is never truly empty. And as your breathing slows, perhaps you feel that hum, not as noise, but as comfort. A reminder that even in the stillness of night, something is always alive, always moving, always whispering just beneath the surface. Sometimes, the quantum world feels like it doesn't just play with space, it toys with time itself. Among the strangest experiments ever imagined are those where the decision of how to measure a particle seems to reach backward, influencing what that particle was doing before the choice was made. These are called delayed choice experiments, and when combined with clever twists, they give rise to what physicists call quantum erasers. To understand this, let's return to the famous double-slit experiment. When a photon, a single particle of light, passes through two slits, it can behave like a wave, interfering with itself and creating a striped pattern on the screen. But if you put detectors at the slits to check which path it takes, the interference disappears. The photon behaves like a particle, choosing one slit or the other. So far, so strange, but at least the order seems clear. The photon passes the slits, and your measurement decides the outcome. In 1978, physicist John Wheeler asked a daring question. What if the choice of how to measure is made after the photon has already passed the slits? Suppose the photon travels through, and only later do we decide whether to observe its path or not. In classical logic, the photon's behavior should already be set by the time it crosses the slits. Yet experiments inspired by Wheeler's idea suggest otherwise. Even when the choice is delayed, the result lines up as if the photon somehow knew in advance whether to act like a particle or a wave. Of course, photons do not have foresight, and nothing supernatural is happening. What the experiments show is that the outcome in quantum mechanics is not determined until measurement. The very act of deciding how to measure is part of the story, and that decision can be made after the photon has already travelled. It is as if the universe leaves the past open, waiting for the future to settle it. The quantum eraser takes this one step further. In this version, information about the photon's path is created but can later be erased. When the which path information exists, even if nobody looks at it, the interference pattern vanishes. But if the information is erased, the pattern comes back, as though the photon's wave-like behavior is restored. It is as if reality asks, is the information knowable? If yes, the photon chooses a single path. If no, the photon lives as a wave. To soften this with a story, imagine writing in a diary. Each entry records events of the day. Now suppose you burn the diary before anyone reads it. Did those details exist in a way that mattered? In quantum physics, the answer would be no. If the information cannot, in principle, be known, then it is as if it never existed at all. The photon goes back to behaving like a wave, as though the choice to erase has rewritten the story. This is why physicists sometimes describe quantum mechanics as caring less about what happens and more about what can be known. Information, or the potential for it, becomes central. A particle's behaviour depends not on your personal awareness, but on whether the setup of the experiment makes the information available in principle. Knowledge, or its erasure, shapes outcomes. It sounds unsettling at first, as if the past could be changed. But the experiments do not actually rewrite history. They reveal instead that quantum events are not fully decided until the chain of interactions, including possible measurements, is complete. The past of the photon is not locked in until the whole context is set. The story of the particle is like a novel that can be edited up to the very last page, its chapters shifting depending on how the ending is written. These delayed choice and quantum eraser experiments highlight just how slippery our ordinary categories can be. We like to think of cause and effect as simple arrows. First the photon passes, then we measure it. Quantum physics reminds us that at small scales, the arrows can loop in surprising ways. It is not that time runs backward, but that the story is not finished until the entire scene is in place. And though these experiments are technical, with beams of light and clever arrangements of mirrors and detectors, their spirit can be held in simple metaphors. Think of a play where the final act is written last, but once it is, the earlier acts seem to have been leading toward it all along. Or think of footprints in the sand that appear different depending on whether you shine a light on them later. The events are flexible until observed in full context. For our purposes tonight, you don't need to wrestle with the mathematics or the detailed setups. It is enough to let the image rest in your mind. Photons waiting for a decision, their story open until the last moment, the past pliable until the future arrives. The universe, it seems, has a remarkable way of leaving things unresolved until everything comes together. This thought can be strangely calming. It suggests that unfinished stories, unanswered questions, and unresolved feelings are not failures. They are simply wave functions waiting to collapse, diaries waiting to be read or burned, patterns waiting for a choice to make them clear. The quantum world teaches us that uncertainty is not an accident but a stage of being, and that resolution comes when the time is right. So as you drift deeper into rest, imagine a diary written in invisible ink, its words fading or reappearing depending on whether you keep it or let it burn. Imagine photons whispering at the slits, their paths undecided until you choose the lens through which to see them. Imagine the universe itself holding open possibilities, patient, unhurried, waiting for you to decide. By the 1920s, quantum mechanics was no longer a handful of curious puzzles. It had become a full-fledged theory, powerful enough to predict the behaviour of atoms, light and matter with astonishing precision. Yet there was still an aching question at its heart. What does it mean? How should we understand a world that seems to exist as probabilities until measured? The interpretation that rose to prominence in those early years is known as the Copenhagen interpretation, named for the city where Niels Bohr lived and worked. It was here, in the quiet halls of Bohr's Institute, that many of the brightest physicists gathered to debate and argue over what quantum mechanics was really telling us. The walls themselves must have felt the weight of those late-night conversations. Bohr's view was both pragmatic and radical. He suggested that we should stop asking what a particle really is before it is measured. The wave function, that cloud of probabilities we've described as mist, should not be thought of as a literal object, but as a tool for predicting the outcomes of experiments. Reality, Bohr argued, is not defined until it is observed. The act of measurement is what turns the potential into the actual. To soften this idea into something more familiar, imagine a book with blank pages. As long as it is closed, the sentences are unwritten. Only when you open to a page and begin to read do the words appear. In Bohr's view, the universe is like that book. The wave function is the set of possible stories, and measurement is the moment when one is chosen and written into reality. This was a startling way of thinking. For centuries, science had assumed that objects have definite properties, whether or not we look. A chair in the room is solid, even if no one is sitting on it. A star continues to burn, whether or not anyone sees it through a telescope. Bohr was not denying this everyday solidity. He was pointing out that at the quantum level, particles do not have definite paths, positions, or energies until something in the world forces them to declare one. Not everyone was comfortable with this. Albert Einstein pushed back strongly. He believed physics should describe a reality that exists independently of our observations. The moon, he famously said, is there even if I am not looking at it. For Einstein, Bohr's interpretation felt unsatisfying, like giving up on the deeper truth of nature. But Bohr countered that asking about reality beyond what can be measured was simply not meaningful in the quantum world. He once told a colleague, "Physics is not about what nature is, it is about what we can say about nature." To Bohr, the task of science was not to reveal hidden essences, but to describe how experiments unfold. The probabilities of the wave function were not shadows of some deeper reality. They were the reality we could talk about. This perspective can sound frustrating, like being told not to ask the very questions that burn brightest. Yet for practical physics, it worked. The Copenhagen interpretation guided generations of scientists, allowing them to calculate, design, and predict with confidence. Lasers, semiconductors, nuclear energy, all emerged in a world where the Copenhagen view was the standard. Think of it like sailing. You may never see the currents beneath the ocean, but you learn to trust the patterns of wind and tide. Bohr's interpretation was like that. Focus on what can be measured, what can be predicted, and do not worry too much about what lies unseen beneath. To make this softer still, picture a sentence not yet written. Until your pen moves, there is no fixed line of words. The potential is there, many choices possible, but only when ink touches the page does one outcome appear. The Copenhagen view tells us that quantum systems are like that. They hold many possibilities, but only when measured by interaction do they write one story. Of course, the debates never ended. For some, the Copenhagen stance is too cautious, too silent on what is really happening. For others, it is refreshingly honest, admitting that our knowledge is limited to outcomes and probabilities. The truth may lie somewhere in between or beyond, in interpretations yet to be imagined. What matters for us tonight is not settling the debate, but noticing the gentle lesson hidden in it. Sometimes, uncertainty is not a flaw, but a feature. The world is not always compelled to declare itself until it must. The openness of possibilities is part of its character. So as you rest, you might imagine the universe as a book with pages that wait blank until turned. You might picture a mist that holds shapes but only condenses when touched by light. You might even think of your own life this way, possibilities held softly until choices bring them into focus. The Copenhagen interpretation, for all its pragmatism, invites us into a kind of humility. It whispers that reality is not always what we expect, not always firm beneath our feet. And yet in that openness there is beauty, because it allows the world to be flexible, to surprise us, to hold more than one story at a time. And as you breathe slowly, letting your eyes grow heavy, perhaps you feel a kinship with that idea, that the day behind you is written, the day ahead unwritten, and the present moment is the quiet act of measurement, the pen pressing softly on the page. The Copenhagen interpretation gave physicists a way to work with quantum mechanics without being paralysed by its puzzles. But not everyone was satisfied with its quiet, don't ask philosophy. Over the years, other interpretations have grown, each offering a different picture of what the quantum world might really mean. They are like different translations of the same poem. The words are shared, but the images they create can feel very different. One of the most famous alternatives is the many worlds interpretation, introduced in the 1950s by Hugh Everett. Imagine you're standing at a crossroads, a path leading left and another leading right. In our usual view of life, you choose one and the other vanishes into what-ifs. But Everett suggested that in quantum mechanics, both paths are taken. The universe itself splits, branching into separate worlds. In one, you walk left. In another, you walk right. Each version is as real as the other, carrying on with its own story. Applied to Schrödinger's cat, this means the cat is not suspended in a fuzzy state of alive and dead. Instead, the universe divides. In one world, the cat is alive. In another, the cat is gone. Both outcomes exist, but in separate branches that no longer meet. It is a daring picture, one that removes the need for mysterious collapse. The wave function never shrinks. It simply unfolds into multiple realities. To anchor this in imagination, think of a novel that keeps splitting into sequels. Each time a decision is made, the book divides, and every storyline is written. You only ever read one version, but somewhere on the shelf, all the others exist too. Many Worlds tells us that reality is like that cosmic library, with shelves stretching endlessly, filled with every possible outcome. Some find this vision breathtaking, others unsettling. It solves the puzzle of collapse, but at the cost of multiplying realities beyond comprehension. Whether those branches are real or simply metaphors is still debated, but the picture lingers in the imagination. The idea that every choice leads not to one story, but to many. Another approach is called objective collapse theories. In these, the wave function does not need an observer to collapse. Instead, it collapses on its own after reaching a certain threshold. Reality is constantly choosing quietly in the background. Imagine a soap bubble that can expand only so far before bursting into a single drop. In these models, superpositions cannot grow indefinitely. At some scale, they resolve themselves into one outcome. The randomness is built into nature itself, like dice being rolled behind the curtain. Objective collapse appeals to those who want a definite mechanism, a real physical process that ends superposition. But so far, experiments have not shown clear evidence of it. The universe remains silent on whether collapse is an active event or just the way probabilities appear. And then there is Qubism, short for quantum Bayesianism. This interpretation is less about the universe itself and more about us, the observers. In Qubism, the wave function is not a physical mist floating around particles. It is a tool for expressing personal beliefs about what outcomes you might see. Just as weather forecasts reflect probabilities based on available information, Qubism says the wave function reflects an individual's knowledge, not an objective state of nature. Imagine two travellers looking at the same mountain, trail. One expects snow ahead, the other expects dry ground. Their forecasts are different, but the mountain is the same. Qubism suggests quantum states are like those forecasts, expressions of belief rather than literal clouds of possibility. When you measure, you are not collapsing the universe. You are updating your expectations, learning more about the mountain you're climbing. This interpretation appeals to those who see science as fundamentally about making sense of experience, not uncovering some hidden essence of reality. It makes quantum mechanics less about mysterious cats or splitting universes, and more about managing expectations in a probabilistic world. Each of these interpretations carries its own tone. Many Worlds is bold and extravagant, filling the cosmos with infinite libraries of outcomes. Objective collapse is firm and mechanical, insisting that nature makes decisions whether or not we look. Cubism is modest and personal, saying that quantum physics is less about the world in itself and more about how we interact with it. Which one is right? No one knows. All three, and many others besides, make the same experimental predictions. Quantum mechanics is a remarkably democratic theory in that way. Different worldviews can sit side by side, all consistent with the facts we measure. For us tonight, it is enough to see them as gentle variations on a theme. You might imagine yourself reading a novel that multiplies into infinite sequels. You might picture a soap bubble that can only stretch so far before snapping into a single drop. Or you might imagine yourself checking the weather, updating your forecast as clouds shift across the sky. Each image is a different way of holding the same quantum strangeness. And perhaps there is a quiet lesson here. Just as physicists live with multiple interpretations without settling on one, so too can we accept that some mysteries remain open. Not every story needs a single ending. Sometimes it is enough to live with parallel possibilities, trusting that the world still unfolds, even when our understanding lingers in uncertainty. So as you breathe slowly, letting your body sink deeper into rest, imagine a library of infinite books, a bubble trembling before it bursts, or a forecast that changes as the sky clears. These are not puzzles demanding solutions, but lullabies of interpretation, ways of saying that the world is richer than one story alone. By now, you've heard the story of Schrödinger's cat, trapped in its strange superposition, alive and not alive until the box is opened. It's a thought experiment meant to highlight the odd gap between the quantum world and the everyday one. But here's the comforting truth. Real cats do not wander around half alive. In practice, the bizarre blur of superposition melts away long before it reaches the scale of teacups, chairs, or pets. The reason is something physicists call decoherence. To soften the word, think of coherence as harmony in music. When a choir sings together perfectly in tune, their voices reinforce one another, creating clear, resonant chords. Quantum systems are like that. Superpositions are delicate harmonies of probability, many possibilities humming in unison. But introduce a noisy crowd outside the hall, honking cars, shouting voices, a street band out of rhythm, and the choir is drowned out. Their harmony collapses into noise. That is decoherence. The environment intrudes, scattering the delicate quantum harmonies until only ordinary outcomes remain. In simpler terms, decoherence is the process by which quantum weirdness fades into classical normality. A tiny particle can stay in superposition when carefully isolated. But in the open world, particles are never alone. They bump into photons of light, collide with molecules of air, interact with countless invisible influences. Each interaction leaks information to the environment, and the system's delicate mist of maybes collapses into one solid story. Let's picture this with something familiar. Imagine you're trying to balance a spinning plate on your finger. In a quiet room, you might keep it going for a while, but if the room is crowded with people brushing past and gusts of wind swirling through, the plate quickly wobbles and falls. Superposition is like that spinning plate, stable only in solitude, fragile when the world leans in. This is why the quantum behaviour we've been exploring is so hard to see in large objects. An electron or photon can stay coherent, that is, remain in its delicate superposed state, if carefully shielded. But a cat, made of trillions upon trillions of interacting particles, is constantly entangled with its surroundings. The noise of the universe drowns out its quantum harmonies instantly. The result is that we only ever see the cat alive or dead, never both. Far from being a disappointment, decoherence is the reason our macroscopic world makes sense. It is the bridge that explains why quantum rules govern atoms and photons, but why tables, chairs, and trees behave in steady classical ways. Without decoherence, reality at our scale would be chaos, superpositions everywhere, outcomes unresolved. With it, the world feels solid, reliable, and safe. Scientists have tested this directly in laboratories. In exquisitely controlled conditions, they place atoms or molecules into superpositions and then watch how quickly those superpositions decay as the system interacts with its surroundings. The bigger the system, or the less isolated it is, the faster the coherence fades. It is a bit like trying to preserve a soap bubble. In still air, the bubble glimmers for a while. Expose it to drafts, dust, or a curious child's finger, and it pops almost instantly. Decoherence is the popping of quantum bubbles. This also explains why building quantum computers is so challenging. Qubits must stay coherent long enough to perform calculations, but the environment is always waiting to interfere. Stray radiation, vibrations, heat, or even background magnetic fields. Engineers go to astonishing lengths to protect qubits, cooling them near absolute zero, shielding them in heavy enclosures, carefully timing each operation. They are in effect trying to keep the choir singing in tune, while the city outside grows ever louder. For us, though, decoherence is not only a technical detail, but also a source of metaphor. It reminds us that clarity often requires quiet. Just as quantum systems need isolation to maintain their superposed harmonies, so too do our thoughts. In a noisy environment, whether physical or emotional, it's hard to stay balanced. But in stillness, coherence emerges. The cat becomes a symbol, not of paradox, but of the delicate balance between possibility and reality. Another way to think of decoherence is with light and shadow. Imagine sunlight streaming through a window, casting sharp patterns on the wall. If the air is still and the glass clear, the shadows remain crisp. But if the air fills with mist, or if the glass fogs over, the shadows blur until they are no longer distinguishable. Superpositions are those crisp patterns. Decoherence is the mist, the blurring that reduces them into ordinary shades. Does decoherence solve every quantum riddle? Not entirely. It explains why cats don't stay half alive, why we don't see superpositions in the macroscopic world, and how quantum possibilities fade into classical outcomes. But deeper philosophical questions remain. Does decoherence mean the wave function itself never collapses, only that interference becomes unobservable? Or does it mean that collapse is simply an illusion, and we live in one branch of many worlds while the others fade from view? Physicists still debate these points. For us tonight, we can leave the arguments aside and rest in the gentle insight decoherence offers, that the world's strangeness is real, but it's softened by the environment into the stable reality we inhabit. Without it, we could not trust the floor beneath our feet or the sky above our heads. With it, we can live in a world both quantum and classical, both mysterious and familiar. So, as you settle deeper into rest, imagine an orchestra playing softly in tune, then hear the city's noise creeping in, blurring the harmony until only one melody remains. Imagine a soap bubble glimmering until the slightest draft pops it. Imagine a cat that is never suspended in an impossible state, but always resting quietly in one outcome or another. Decoherence is nature's way of making sure the world writes itself clearly, even if the ink at its base is probability. And perhaps this is also a lullaby for you, that beneath uncertainty and noise there is always resolution. The world finds a way to settle, to choose, to rest, and so can you. When most of us first learn about the building blocks of the universe, we imagine them as tiny marbles, little beads of matter bouncing around and colliding. It's a comforting picture, solid, simple, and easy to hold in your mind. But as physicists dug deeper into the quantum world, that image began to dissolve. The closer they looked, the less particles resembled hard balls, and the more they looked like ripples, excitations, and disturbances of something even more fundamental. That something is the world of quantum fields. Instead of imagining the universe built from countless marbles, picture it as a vast stage spread invisibly across space. Every kind of particle we know corresponds to a field that permeates the cosmos. The electron field, the photon field, the quark fields, all of them stretch everywhere, unseen but always present. Particles are not separate, independent things. They are local excitations of these fields, tiny ripples rising briefly in the stage before fading away again. To soften the idea, think of a pond on a calm day. Beneath the surface lies still water, patient and unbroken. Toss in a pebble, and ripples form, spreading outward, cresting and falling. The water was always there, the stage that allowed the ripples to exist. In the same way, fields are the calm background. Particles are the ripples that appear when energy disturbs them. This picture is strange but powerful. It means that even the emptiest patch of space is not truly empty. The electron field is there, the photon field is there, and so are all the rest, invisible blankets covering the cosmos. At any point with the right spark of energy, a ripple can form, an electron emerging from the electron field, a photon from the photon field, and so on. One of the most striking lessons of this view is that particles are not permanent marbles. They are temporary ripples, localized vibrations that can be created and destroyed as the field is stirred. This is why high-energy collisions in particle accelerators can transform one kind of particle into another. When two ripples crash together, their energy reshapes the field, and new ripples appear in different forms. It is less like smashing billiard balls and more like striking chords on a guitar. The vibrations can blend, shift, and give rise to new notes. This framework is called quantum field theory. And though the phrase may sound heavy, you can think of it as simply taking the idea of waves seriously. Waves not only in water, not only in air as sound, not only in light as ripples of electricity and magnetism, but waves in the very fabric of reality. Everything we see, touch, and feel arises from these hidden seas of vibration. Perhaps the most poetic aspect of fields is their universality. The electron field that makes up your body is the same electron field filling the space between stars. The photon field that allows light from a candle to reach your eye is the same photon field that lets sunlight travel across 150 million kilometers of space. These fields are not confined, they're everywhere, stretching without end. There is also the Higgs field, discovered experimentally in 2012 through the particle named after it, the Higgs boson. The Higgs field is what gives many particles their mass. Without it, electrons would have no weight, quarks would drift without substance, and atoms as we know them would never form. You can imagine the Higgs field as a kind of invisible molasses spread across the universe. Particles moving through it are slowed down, given heft, made into something rather than nothing. Without this field, the cosmos would be structureless, a light show with no anchors. Thinking of the universe as fields instead of marbles may feel unsettling at first. But there is a quiet beauty in the image. It says that beneath the buzzing world of particles there is a continuous stage, a set of hidden fabrics from which everything emerges. You are not made of isolated marbles, but of ripples sustained by fields that span the whole universe. In a sense, you're already connected to the stars by the very fields you share. If you prefer a gentler metaphor, imagine lying on a trampoline stretched taut. When you tap the surface, ripples spread. Each ripple is temporary, but the trampoline itself remains. The fields are the trampoline holding steady across space. Particles are the ripples dancing on top. This picture also hints at why quantum mechanics and relativity, the physics of the very small and the very large, sometimes clash. Fields must be both quantum, filled with fluctuating ripples, and relativistic, spreading consistently across space-time. Marrying these two ideas is difficult, but quantum field theory achieves it beautifully, at least for most of nature's forces. As you listen, you don't need to hold on to the technicalities. It is enough to rest in the imagery. Ponds and ripples, trampolines and waves, invisible blankets stretched across the cosmos. All matter, all energy, all particles are brief disturbances in deeper fields. Even the chair you sit on and the breath you take are ripples sustained by invisible seas. And perhaps that is a soothing thought for bedtime, that beneath the noise and clatter of daily life lies a stage of deep stillness, a set of fields steady and omnipresent, carrying the ripples of existence. Just as the pond beneath the ripples remains calm, so too does the universe rest beneath the buzz of particles. So as you drift towards sleep, imagine yourself as a ripple on that cosmic pond, rising and falling gently on a field that stretches everywhere. The fields hold you, just as they hold the stars, weaving everything into a single fabric. In that sense, you're not separate from the universe, but part of its endless, shimmering stage. If quantum fields are the stage upon which reality unfolds, then the Standard Model is our current score for the orchestra of particles and forces. It is not the ultimate truth of the universe, but it is the most successful description we have so far, a framework that has guided decades of experiments, predicted discoveries, and explained almost everything we see in the subatomic world. To soften the image, imagine a grand symphony hall. The musicians are already seated, each family of instruments tuned to play its part. Strings, brass, woodwinds, percussion, all distinct, yet all necessary. The Standard Model is like that orchestra. Each section corresponds to a family of particles, and the forces that bind them are like the rhythms that keep the music together. At the heart of this orchestra are the fermions, the particles of matter. They are the violins and cellos, the oboes and clarinets, the instruments that form the texture of the music. Fermions include quarks, which combine to make protons and neutrons, and leptons, which include the electron and its kin. These particles are the basic building blocks, the raw notes from which atoms, molecules, and all of us are composed. But no orchestra can play without rhythm and coordination. That role belongs to the bosons, the force-carrying particles. They are like the conductors and percussionists, keeping time and binding the music together. The photon carries the electromagnetic force, binding electrons to atoms and giving us light. The gluon carries the strong nuclear force, gluing quarks together inside protons and neutrons. The W and Z bosons carry the weak force, responsible for radioactive decay and the processes that power the sun. And then there is the quietest player, one who was only confirmed recently, but who underlies the entire performance, the Higgs boson, linked to the Higgs field. Its role is not to strike a loud note, but to provide weight, to endow particles with mass. Without the Higgs field, fermions would remain massless, slipping through the universe without form, unable to clump into stars or planets. With it, the universe gains heft, structure, and stability. You can imagine the Higgs field as a kind of invisible molasses spread across the stage. Particles moving through it slow down, gaining substance, becoming part of the symphony. When you step back, the Standard Model really does look like a score. There are 12 fermions in total, 6 quarks and 6 leptons, each playing its own melody. There are 4 force carriers, photon, gluon, W and Z, weaving the harmonies, and there is the Higgs field, the quiet background tone that makes the rest possible. What makes this so remarkable is how well the symphony performs. The Standard Model has predicted outcomes with astonishing accuracy. Experiments at particle colliders, like the Large Hadron Collider in Geneva, have confirmed its notes again and again. The discovery of the Higgs boson in 2012 was like hearing the long-awaited final instrument join the orchestra, completing the set. And yet, even in its beauty, the Standard Model is incomplete. It does not include gravity, the force that shapes planets and galaxies. The graviton, if it exists, is not part of the score. Dark matter and dark energy, which make up most of the universe's content, also remain absent. It is as if we can hear the orchestra playing beautifully, but faint notes from backstage hint at a larger piece of music we have not yet learned to read. Think of sitting in a concert hall as the orchestra plays a masterpiece. Every section is clear, the harmony is precise, yet in the pauses you sense something else. A distant choir, a hidden rhythm, a melody that belongs to a larger composition beyond what you hear. That is where we stand with the standard model. It explains so much, but not everything. For bedtime reflection, there is something soothing in this. It means that the universe is knowable, to a point. We can describe its particles and forces with exquisite detail. But it also means there is mystery left, music still unheard. The gaps remind us that science is an unfinished symphony, one that continues to grow and evolve. To ground this in imagery, imagine yourself as part of the orchestra. The atoms in your body are fermions held together by bosons, given mass by the Higgs field. Every thought, every heartbeat, every breath is a phrase of music played on this cosmic stage. You're not merely listening to the standard model symphony, you are one of its instruments. And perhaps the most calming thought is this: the symphony has been playing since the first moments of the universe. From the fireball of the Big Bang to the quiet breathing of tonight, the same particles and forces have carried the tune. The score may be incomplete, but the music is ongoing, and you are part of its resonance. So as you rest now, imagine the orchestra tuning down for the evening. Strings quiet, horns fading, the conductor's baton lowering softly. The music does not end, but it shifts to a lullaby, gentle and low, carrying you into sleep. The standard model may be unfinished, but its song, the song of particles and forces, will play on, weaving you into its harmony. Among the many parts of the standard model, there is one jewel that shines especially bright: quantum electrodynamics, or QED for short. It is the theory that describes how light and matter interact, how electrons and photons, particles of electricity and particles of light, talk to each other across space, and it has earned a reputation as the most accurate theory humanity has ever created. At first glance that might sound abstract, but to soften it, think of QED as a conversation. Electrons and photons are like old friends exchanging words, glances and signals. Every time you turn on a lamp, charge your phone, or see the glow of a candle, you're witnessing countless such conversations happening at once, each guided by the rules of QED. The strange beauty of this theory is not only in what it says, but in how it works. Physicist Richard Feynman, one of QED's greatest champions, realized that the interactions between particles could be drawn as little sketches, what we now call Feynman diagrams. These doodles look almost playful. Straight lines for electrons, wavy lines for photons, meeting at points where interactions occur. Yet behind their simplicity lies staggering power. By following the rules of these diagrams, physicists can calculate probabilities of real experiments with incredible precision. Imagine doodling stick figures on a napkin and then finding that those doodles predict exactly how often sparks will fly from a power line, or how precisely an electron's magnetic field will tilt. It sounds absurd, yet this is what QED provides: a sketchbook that maps the behaviour of the universe to 10 or even 12 decimal places of accuracy. One famous example is the magnetic moment of the electron, a tiny property describing how the electron acts like a little compass needle. When measured in experiments, the number matches QED's prediction to more than 1 part in a trillion. To picture that accuracy, imagine measuring the distance from Earth to the Moon and getting it correct to within the thickness of a human hair. That is the level of agreement between theory and reality. No other scientific framework has ever achieved such perfection. Why does it work so well? Because QED takes seriously the fuzziness of the quantum world. Instead of imagining a single path or outcome, it adds up all possibilities. In Feynman's playful words, an electron can take every path at once: straight lines, zigzags, loops, detours, and the final result comes from summing over them all. The diagrams are not just drawings, they're reminders that reality is a tapestry woven from countless quantum possibilities, all interfering and cancelling until a clear outcome appears. The power of QED is not confined to textbooks. It underlies technologies that define modern life. The circuits in your computer, the lasers in your DVD player, the precise measurements in GPS systems. All of them depend on QED's ability to describe how light and matter interact. Each time you swipe a credit card or watch a fibre optic cable flash data across continents, QED is at work behind the scenes, invisible yet indispensable. And yet, for all its triumphs, QED still leaves us with mystery. It describes the electromagnetic force with unmatched precision, but it does not by itself explain the strong nuclear force, the weak nuclear force, or gravity. It is a virtuoso soloist in the orchestra, dazzling but incomplete. To soften this into an image, picture a violinist playing so perfectly that every note matches the score to impossible accuracy. The audience is breathless, and yet you know that the rest of the orchestra must eventually join in, or the full piece will remain unfinished. QED is that violinist, a master performance waiting for its companions. Even its method of calculation, though wildly successful, has an air of magic. The sums over possibilities sometimes produce infinities, answers that make no sense. Physicists learn to tame these infinities through a process called renormalization, stripping away the meaningless parts and leaving the predictions that match reality. The name sounds dry, but the process is almost alchemical. Infinities in, perfect numbers out. Feynman himself joked that it was a kind of dippy process, but it worked, and it worked better than anyone dared hope. For bedtime reflection, perhaps the most soothing part of QED is its humility. It does not claim to reveal the deepest secrets of existence. It says instead, if you want to know how light and matter interact, here is a recipe that works, tested to the edge of precision. It is practical, honest, and astonishingly reliable. Like a carpenter's tool worn smooth by generations, it simply fits the task. And maybe that is a quiet lesson for us too. Perfection need not be grand or final. It can be found in the careful accuracy of small things, a note struck in tune, a compass pointing true, a prediction matching reality down to the tiniest detail. QED shows us that the universe, in all its strangeness, can sometimes sing with absolute clarity. So as you settle deeper now, imagine electrons and photons chatting in the dark, their conversations sketched as doodles in a cosmic notebook. Imagine an orchestra with one soloist playing perfectly while the others wait their turn. Imagine measuring the moon's distance to within a hair and knowing that your calculation is right. These are the images of QED, precise, playful, and quietly beautiful. And as you breathe out, perhaps you feel comfort in that precision, that even amid the uncertainties of life, there are places where the numbers line up, the notes ring true, and the universe answers with a soft, exact yes. We've wandered through the theories, the experiments, and the interpretations of quantum physics. But one of the most soothing realizations is this. Quantum mechanics is not just locked away in laboratories or hidden inside particle accelerators. It is woven into the world around us, present in the technology we use, and perhaps even in the living creatures that share the planet with us. The most obvious place is technology. Quantum computing is still in its infancy, but even in these early stages, it is already teaching us how fragile and powerful superpositions and entanglements can be. Unlike the billions of classical bits inside your laptop, each either 0 or 1, a quantum bit, a qubit, can be both 0 and 1 at once. The power lies not in a single qubit, but in the collective harmony of many, linked by entanglement, Together they can explore a vast space of possibilities all at once. The challenge, as we've seen, is keeping them stable. Decoherence is always waiting, like a draft that pops soap bubbles. Engineers protect qubits by cooling them near absolute zero, shielding them from noise, and using clever error correction to patch over mistakes. These machines are still noisy and limited, like the fragile first airplanes of the early 20th century. They cannot yet cross oceans of computation, but they have proven that flight is possible. Why do we chase them? Because some problems lie far beyond the reach of classical computers. Simulating molecules, for example, grows impossibly complex as the molecules become larger. A quantum computer, speaking the same quantum language as the molecules themselves, could handle these problems with elegance. From designing new medicines to developing advanced materials, the possibilities shimmer like constellations not yet reached. But quantum mechanics is not only at work in machines, it may also whisper inside life itself. Take the humble robin, a bird that migrates across continents. Experiments suggest robins may navigate using Earth's magnetic field, guided not by iron in their beaks, but by quantum entanglement inside special proteins in their eyes. The idea is that pairs of electrons inside these proteins become entangled, and their delicate state shifts depending on the angle of Earth's field. The bird literally sees a pattern in starlight shaped by quantum effects, a compass painted invisibly across the sky. It is a breathtaking thought, that a creature no larger than your hand carries a built-in quantum sensor, honed by evolution long before humans discovered the theory. When you picture a robin in flight, drifting steadily across vast distances, imagine its eyes reading invisible cues whispered by entangled particles. Quantum mechanics, not just physics, but biology. Plants too may use quantum tricks. In photosynthesis, sunlight is captured and funneled into chemical reactions. For years, it was puzzling how energy moves so efficiently, with almost no loss. Studies suggest that quantum coherence, the wave-like spreading of energy across multiple paths, allows the plant to test many routes at once, guiding the energy along the most efficient trail. Imagine a traveller entering a maze and somehow walking every path at once, choosing the exit instantly. That is what quantum mechanics may grant to leaves and chloroplasts. Even our sense of smell has been linked to quantum ideas. One proposal is that when an odour molecule enters your nose, electrons tunnel, slipping quantum style, through the molecule. The tunnelling depends on the molecule's vibrations, giving rise to distinct scents. If true, it means that every breath you take is a subtle conversation between biology and quantum tunnelling. Of course, these areas of quantum biology are still under study. Not all scientists agree on how strong the evidence is, and more experiments are needed. But the very possibility is soothing in its poetry, that life itself, from the flight of birds to the drink of sunlight in leaves, may rely on the same quantum rules that govern stars and particles. And at the bedrock of it all lies quantum, randomness. At the smallest scales, events are not strictly determined. A particle's decay, a photon's arrival, an electron's spin, each is decided by probability, not certainty. This might sound unsettling, as though the world is built on chance, but in truth, quantum randomness is astonishingly reliable. Though individual events are unpredictable, the statistics over many events are exact. You cannot say when one atom will decay, but if you measure 1,000,000, the pattern will line up perfectly. To bring this into an everyday anchor, think of raindrops. You cannot predict the path of one drop down a window pane, but you can predict that after a storm, the bucket outside will be filled to a certain level. Quantum physics works like that. Chaos in the small, order in the whole. For us, there is something reassuring in this balance. The universe allows spontaneity at its foundation, yet in the long run the patterns hold steady. Stars burn, seasons turn, life continues. Randomness at the micro level becomes stability at the macro level, a paradox that makes the world both mysterious and trustworthy. So as we close this journey, picture a robin steering by invisible starlight. a leaf guiding sunlight with uncanny efficiency, and a molecule of perfume carrying its scent through the tunneling of electrons. Imagine a quantum computer glowing faintly in its cold chamber, whispering in the language of superpositions, and imagine the steady rain of quantum randomness, each drop unpredictable, yet the river always flowing true. Perhaps that is the final lullaby quantum physics offers, that mystery and reliability can coexist, that the smallest events are free, yet the whole is steady, that life, technology, and the stars themselves all hum to the same quiet rules.